Assalamu alaikum everyone. Today we will explain chemical reaction engineering chapter 1. So we will start with the introduction. All industrial chemical processes are designed to produce economically desired product or useful product from starting materials, which are raw materials like crude oil. So the process begins with the raw materials like crude oil. They undergo physical treatment steps. So when they are physically processed, they are ready to be treated chemically. When they are in the chemical treatment steps, they undergo chemical transformation inside the reactor. And here, whereas the actual chemical reaction happens, like converting crude oil into fuels, then they also undergo further physical treatment steps, so to be purified or to be separated. Then the products are obtained or produced. And if you notice, you will see that there is an arrow mark starting from here to that box. And so here where the recycle will happen, if there is any unreacted materials, they will be sent back to the physical treatment steps and the whole process will start again. Then we will know chemical reaction engineering, which means the study and application of how we design a reactor, how to design a chemical reactor. So it is the synthesis of all these factors with the aim of properly designing a chemical reactor. And to know the ability of a reactor, we must know kinetics, contacting pattern, and performance equation. Kinetics means how fast things happen, and contacting pattern means how materials are flowing and mixing with each other in the reactor. Then performance equation, which relates input to output, or it relates the raw materials with the products. Then contacting pattern on how materials flow through and contact each other in the reactor, how early or late they mix, their clumpiness or state of aggregation. State of aggregation means whether the material is solid, liquid, or gas. And clumpiness means when the material doesn't dissolve or doesn't mix, like solids and non-coalescing liquid droplets. Then kinetics, or how fast things happen. If very fast, then the equilibrium tells what will leave the reactor. And if it's slow, then the rate of chemical reaction and mass transfer too will determine what will happen. When designing a reactor, it isn't an easy process because we should consider few things, like whether it is economically suitable. So the goal is to find the best design, one that makes the product at the lowest total cost. Then it's not just about the reactor being cheap. So the main goal here, or the challenge, is to choose the best design, which is the cheapest. But we don't need to just minimize the cost of the reactor itself, but to minimize the overall process cost. For example, if we have a reactor which is cheap, it may seem good, but if the product coming out requires expensive purification, so the total cost will be higher than the initial one. So we must consider the economics of the overall process, or the overall cost. Then engineers use knowledge from many fields. We must know thermodynamics, chemical kinetics, fluid mechanics, heat and mass transfer, and economics. Also, things must be considered. Chemical kinetics is the study of how fast chemical reaction happens. So we must know reaction rates, reaction mechanisms. Chemical reaction engineering combines chemical kinetics, the design of reactors where these reactions take place, and the two key points to produce all industrial chemicals are kinetics and reactor design. And we must ensure that reactions happen safely and economically. Then knowing kinetics and reactor design is what sets chemical engineers apart from other types of engineers. So knowing kinetics and reactor design design also are the key points that distinguish chemical engineers from other engineers. Then choosing the right reaction system, safe and efficient, is often the key to success or failure of a chemical plant. The rate of a chemical reaction depends on certain variables. These variables can be different depending on whether the reaction happens in a single phase, homogeneous, or in multiple phases. So, in homogeneous system, temperature, pressure, and composition. So if we increase the temperature, the faster the reaction. Then pressure. If we increase the pressure, that means more molecules in a small area. So then there will be more collisions, then the faster the reaction. Composition, the concentration or amount of each reactant. More reactant means faster reaction. In heterogeneous system, more than one phase is involved, hence the problem becomes more complex. So it will not be simple like in homogeneous system. Material may have to move from phase to phase during reaction. Transfer play important roles in determining heterogeneous reaction rates. So they are important in determining the heterogeneous reaction rates, and it was written here that they are important while choosing the chemical reactor. There are different forms of reaction rates, like if it's based on unit volume of reacting fluid, it will be the moles, the number of moles formed divided by the product of volume and time. And if it's unit mass of solid and fluid solid, it will be the Ri dash will be equal to the number of moles divided by mass of solid and time. Then based on unit interfacial surface in two fluid systems, or based on unit surface of solid and gas solid, Ri dash dash will be equal to the number of moles divided by the product of surface and time. Then unit volume of solid and gas solid systems, Ri 3 dashes will be equal to the number of moles divided by the product of volume of solid and time. So you should specify the volume here. It is SVS. Then based on unit volume of reactor, if different from the rate based on unit volume of fluid, then Ri 4 dashes will be equal to the number of moles divided by the product of volume of reactor, not volume of the reacting fluid. Like in the first case, it is divided by the volume of reactor and time. Then you should memorize these things. After that, based on unit volume of reacting fluid, as we said. However, in heterogeneous, we will have two laws. The first one on unit volume of reacting fluid. The second one on unit volume of fluid, because in heterogeneous they are not identical. However, in homogeneous systems, the volume of fluid in the reactor is often identical to the volume of reactor. In such a case, V and VR are identical or the same. Speed of chemical reactions, moles of A disappearing per meter cube of thing, which is the volume, times time. Classification of reactions, how to classify reactions. If it's homogeneous, then we will have just one phase. However, in heterogeneous, at least we should have two phases. And the most useful scheme is the breakdown according to the number and types of phases involved.